Hello everyone. Our today's subtopic of discussion under the lecture series of thermodynamics in its fifth lecture are zeroth law of thermodynamics and basic concepts about temperature, heat and work and their definitions. So let's start with the zeroth law of thermodynamics. Actually there are four laws of thermodynamics. We have already had our basic concepts, the mathematical relationships and the functions regarding the fundamental concept of thermodynamics. Now we move on to the laws of thermodynamics, and out of the zeroth law, first law, second law and third law, we have to start from the zeroth law. And this zeroth law states that if two thermodynamic systems are each in thermodynamic equilibrium with a third one, then they are in thermal equilibrium with each other. Okay, so we have to elaborate this with a diagram here. This diagram shows that there are three systems. System A and system B are independent, but both of them are connected with system C, so that system A is at thermal equilibrium with system C. Look, number one, system A and C are in thermal equilibrium. Number two, on the other hand, system B and system C are in thermal equilibrium with each other. Then what we can conclude according to the zeroth law, we can conclude that the system A and system B are also in thermal equilibrium with each other. Okay. So what about the physical significance of the third law, of the zeroth law of thermodynamics? Okay. So the physical significance is systems are said to be in thermal equilibrium if there is no heat transfer. So if heat transfer takes place among two systems, then we can conclude that there is no thermal equilibrium. But if after getting them into contact with each other, there is no heat, though there is no transfer of heat, then we come to the conclusion that they have attained thermal equilibrium. Next, systems that are in thermal equilibrium exist at the same temperature. That means if two systems there is no heat transferred between each other, then also we can conclude that their temperatures must be same. And finally, if two bodies in contact with each other have same temperature, they are in thermal equilibrium. Or that means the reverse statement. What is the reverse statement? This is the statement: systems that are in thermal equilibrium are same temperature. The reverse statement should be what? If they have same temperature, they are also at thermal equilibrium. That is said in this third point. So if two bodies in contact with each other have same temperature, then they are in thermal equilibrium. Okay. Now let's elaborate or throw some more light on the zeroth law of thermodynamics by citing two examples. In the first example, if we put food in the refrigerator overnight, then that food is in thermal equilibrium with the air of that refrigerator. Heat no longer flows from food to the air or from air to the food, and this state is known as thermal equilibrium. So when you keep the food item inside the refrigerator, the heat energy is absorbed by the compressor of the fridge and it is thrown out of the system, and afterwards the temperature of that food item becomes equal to that of the internal air of the refrigerator. That means it attains, after some time it attains what? The thermal equilibrium with the internal air of the refrigerator. Okay, so this is one example where after attaining the thermal equilibrium, no heat transfer would occur between food item and the internal air of the refrigerator. Next example is very beautiful example. Suppose we have two glasses of water, one having hot water and the other one having cold water. Now if they are left in the table for a few hours, they will attain thermal equilibrium with the temperature of the room. That means here we can say system A is the cold water, system B is the hot water, and system C, what is system C? System C is the surrounding or the atmosphere of the room. Okay. Now after some time, system A and C, that means the atmosphere and the cold water have reached same temperature. That means actually the cold water absorbs some heat energy from the surrounding. It takes away some heat energy from the surrounding and attains the temperature of the surrounding. On the other hand, the hot water loses some energy, or it releases some energy to the atmosphere, so that it can also attain the temperature of the atmosphere. Suppose the temperature of the atmosphere is 25 degrees Celsius and the temperature of the cold water is 20 degrees Celsius, or on the other hand the hot water is 30 degrees Celsius. Okay, so after some time you will find that temperature of both the glasses have become 25 degrees Celsius, that is equal to that of the atmosphere or the room temperature. Okay, so you are measuring the temperature with the help of thermometer of the glass 1, that is the cold one, and glass 2, that is the hot one. You will find both the temperature of system A and B, that is the hot water and the that is the cold water and hot water, are same. That means they have same temperature. That means they are also in thermal equilibrium with each other. That means the hot water and the cold water are also in thermal equilibrium with each other. And know, if they are kept in contact with each other, then no heat energy will be transferred among them. Okay, or no temperature will be recorded in both of them. So temperature is such a parameter which actually differentiates thermodynamics from other sciences. Okay, that is why we have got to define this parameter temperature from the perspective of the zeroth law of thermodynamics. Okay, so temperature is such a property that distinguishes thermodynamics from other sciences. This property can distinguish between hot and cold. Okay, so we definitely have to define temperature from the perspective of the zeroth law. Okay, so what is the definition? The definition is when two or more bodies at different temperatures are brought into contact, then after some time they attain a common temperature and they are said to exist in thermal equilibrium. I repeat it, when two or more bodies at different temperatures. So we have two bodies which do not have the same temperature. Okay, so they are brought into contact. That means they are now touching each other, or we have made a connection in between them. Then after some time they attain a common temperature. That means after some time what would we find? We'd find that the temperature of both the bodies have become same. That means they are said to exist in thermal equilibrium. In that state, no temperature change will be recorded or no heat transfer would occur between them. So that's all about the zeroth law of thermodynamics, its example, its elaboration, and the definition of temperature from its perspective. Now let's move on to our next topic, which is about heat energy. So what is the concept of heat? The concept of heat is that heat is the form of energy that is transferred between systems or objects with different temperatures. So heat energy will be transferred only from among the bodies which have different temperatures. Okay, suppose you are putting your hand in water. Suppose the water is cold, then heat will be absorbed from your hand by the water. Suppose you are putting in your hand some hot water, then you are absorbing some heat from the water. So this is simple the concept of heat energy. It is irrespective of the size of the body, it is irrespective of the overall heat content of the body. It is only a function of temperature. If the temperature is higher, then if it is it is coming into contact with a body which is lower temperature, then heat definitely would transfer from the higher temperature body to the lower temperature body. Okay, and that is why another name of heat energy is called thermal energy. Okay, so how would we symbolize heat? We symbolize heat as Q, and its overall change is delta Q. Or sometimes if its change is small change, then we can also describe it as dq. So when heat energy is transferred from system to surrounding, then heat change is called what? So it is convention, it is called negative. So look at this point very minutely, very carefully. System is releasing some heat and this heat energy is being absorbed by the surrounding. And what is the convention of denoting delta Q? The convention of denoting delta Q is negative. Okay, so delta Q should be negative. And if heat is transferred from surrounding to system, that is, the system is absorbing some heat, that is, the system is getting hotter, okay, then in that case delta Q should be positive. Suppose a glass of water containing cold water, okay, so that is definitely an endothermic system because heat is being absorbed there, okay. In that case delta Q should be positive. On the other hand, if you put a hot water glass on the table, then heat will be released by the system towards the surrounding, and in that case heat is lost. That means delta Q should be negative. And you must be curious to know what is the type of function about Q, whether it's a state function or it's a path function. Definitely heat is not a state function, it is a path dependent function or simply a path function. That is why dq or delta Q are not perfect differentials or exact differentials. Okay, so that's about the concept of heat. Now move on to the concept of work. Okay, like heat, work is also another path function. That is, only there are two path functions. One is heat, another is work. Okay, work is denoted as W and its small changes as denoted by dW. Okay, and sometimes dW is also written as W. Now here you just have a look that how is the convention of writing W. When work is done by the system, then W is negative. Okay, this is SI convention. And when work is done on the system, that is surrounding is doing work, then W should be positive. Suppose take the example of expansion of gas and compression of gas. When gas is being expanded, then the piston is being pushed upward by the system, isn't it? The gas inside the piston is pushing the piston upward. So the system is working. In that case, you have to denote this in the negative sign. On the other hand, when surrounding is working on the system, that means the system is getting compressed, the gas is getting compressed. So the piston is being pushed inward or downward by the surrounding. Okay, in that case the system isn't at all doing the work. The work is being done by the surrounding, and in that case W should be written as the positive sign. And definitely W, since W is a path function, so dW or delta W is not a perfect differential or an exact differential. Okay, now let's we have to put another point that dq and dW are sometimes written as d cross q and d cross w respectively. Why? Because simple. The reason is simple, because they are path functions and their differentials are not exact difference. So what is the reason? Q and W are path functions and hence their differentials are not perfect differentials. That is why dq is sometimes written as d cross q and dw is sometimes written as d cross w. Okay, now move on to definition of work. So if I ask you what is the definition of work, you would answer that, sir, the definition of work is the force into the displacement. Is it the correct definition? I would say no. You may also say that, sir, the definition of work is that some electrical particle is moving, electrical particle having charge q coulomb moving in the field of v volt, so its electrical work is q into v. Is it the definition of work? No, these are actually the mathematical forms of work. What is the exact definition of work? The exact definition of work is the multiplication of intensity factor and the capacity factor. So this is the exact definition of work. Okay, so let us elaborate this with some examples. If it is the kinetic work, then it is the intensity factor is force and the capacity factor is displacement. Try to match the color of the statements here. This work is written as violet color, written in the violet color. The intensity factors are written in the copper sulfate color, that means the blue color. Okay, vitriol color, it is known as the vitriol color. And the capacity factor is written here in the green color. Okay, so here you can easily differentiate them. So the work, what is the type of work? If it is kinetic work, then the intensity factor is force, and the capacity factor is displacement. And what is the mathematical form? It is minus F into dH. Minus F, why is the minus sign? Because it is working against the direction of work. Okay, so this is the intensity factor and dH is the capacity factor. This is the movement of the object. Okay, gravitational work, gravitational force into the altitude of the body up to which it is raised. Okay, so the gravitational force is minus mg. Okay, and h is the body raised. Another thing, the minus signs are also can be explained from the perspective that since work is being done by the system, that is why these negative signs are given here. Okay, now move on to the third example. This is electrical work. Electrical work is what is the intensity factor? Intensity factor is the potential difference or the electric potential. And what about the capacity factor? Capacity factor is the charge of the body. Okay, so minus V into Q. V is volt, Q is coulomb. Okay, mechanical work. This is very important. This point would be utilized throughout this chapter of thermodynamics. Okay, so keep it in your mind that dW is minus P into dV. Okay, take the example of expansion of gas within a cylinder. Okay, so the pressure is actually inside from the outside the piston towards the inside the piston, is inside the cylinder, isn't it? And the movement of the piston in which direction? In the opposite direction of the pressure. So you are pushing actually the surrounding is pushing the piston from upward to downward, while the system is pushing the piston from downward to upward direction. And since the piston is moving in the upward direction, that is opposite to the pressure, that is why this pressure is given the negative sign. That is the explanation of giving the negative signs in all the mathematical definitions of work. Okay, and dV is the volume change. And try to just work out this. Put the dimensions of pressure and volume. You would find that it is getting the dimension of work, isn't it? Pascal into volume. Pascal means what? Pascal means the pressure, actually the unit of pressure. So what is the unit Pascal? Actually it is Newton per meter square. And Newton is what? Newton is kg meter per second square. And if it is divided by meter square, then it becomes kg per meter per second square. When kg per meter per second square is multiplied by meter cube, then it becomes kg meter square per second square, isn't it? So what is the dimension of kg meter square per second square? It is the dimension of definitely work, isn't it? Length into mass into length into time square inverse. Mass into length square into time square inverse. Kg meter square per second square. Okay, and this is definitely the definition of joule. So definitely this is dW, this is work. When pressure is multiplied with volume change, this is work. Okay, and since the system is working, it is minus P dV. So this relationship is very important relationship. It would be utilized throughout. And finally, elastic work is force constant into change in length. So minus F is the force constant and dx is the change in length. So that's all about the concept of work and its definition and their different mathematical relationships. So that's all for today. Thank you. Have a nice day.